Yeah, I work at the University of Vienna, and I'm going to give you an overview of our plans for making a Lagrangian reanalysis dataset. So first I'll give you, first I'll give you a short motivation, and then I'll go a bit more into detail in what our dataset will look like and how we produce it. Meteorological reanalysis are widely used datasets in atmospheric research, but they are all of Eulerian nature, where data is given at fixed points, like for example the ERA 5 reanalysis. And the thing is that when studying transport of air, it could be beneficial to approach a problem from a more Lagrangian way, where the data is stored in moving air parcels instead of fixed locations. So we are not making a Lagrangian dataset from scratch, but we are using the ERA 5 reanalysis and convert it to a dataset where air parcels are the main focus instead of a grid. So it contains the same information, but it is presented in a different way. So by following the evolution through time of these air parcels, then we can study the mass, moisture, and energy transport through the atmosphere. For example, you could study the dynamic processes that lead to extreme events in temperature, wind, and precipitation. The goal is to publish a Lagrangian dataset where air parcels are being followed through the atmosphere for about the last 50 years. These particles, they are distributed according to the density of air. So you have more particles close to the ground than in the stratosphere, but the mass of each particle is the same and it stays constant over time. It doesn't lose mass. And then this data will be is printed into netcdf files at every hour. This doesn't only include the 3D positions, but also some meteorological data which is interpolated from the ERA 5 dataset, which are listed here. So we both compute instantaneous values and values average over the past hour. So the instantaneous meteorological values like pressure and temperature, etc., you could directly get from the ERA 5 data as long as you have the positions of the air parcels. So any data that is not listed here can be easily retrieved from the ERA 5 dataset. The average values, however, they contain information about the trajectory of the air parcel for the last hour. So every 10 minutes, the positions and other values, they are saved and then averaged after the hour has passed. So in the graph, you can see that what this would look like. So instead of having exact values at each time step, as shown on the left, you get the average of all yellow points on the right. So then, well, at a half of the time step then. And this information could be important if there's a lot of turbulence, or for example, where the instantaneous values are not very representative anymore. Next. So the model we use to do this translation with is called Flexbot. We use the newest version, which is Flexbot 11, which we are working on to publish in the near future. Flexbot uses, it uses the meteorological data to compute the trajectories of air parcels and then interpolates important properties of the Eulerian data set to positions of these parcels. And then it includes also a parameterization of turbulence and convection. We updated Flexbot to work well for our purpose, which means that it is parallelized with OpenMP. We reduced the number of internal interpolations that is necessary for calculating the trajectories, thereby increasing the accuracy. I will show you a bit more about that in the next slide. And we made it possible to have the output of the particle data in netcdf format, which was previously only possible for gridded output. And since for most Flexbot purposes, like tracing aerosols, you only need gridded output. But for LARA, we want to store the data following the air parcels. So one of the main issues we had with Flexbot 10.4 version, which is the official release, the newest one, is that the air parcels, they no longer follow the air density profile of the atmosphere after a while, which is problematic if you want to trace air for longer periods. as we are doing. So, so here on the left side, you see the difference between the particle number densities and the actual air density as given by the ERA 5 data after only 9 weeks of running the model. The y-axis shows the height about above ground level in meters, and on the x-axis is the latitudes. Then the values are average over a whole week and over all longitudes. And red means too many particles, blue means not enough particles. So we end up with accumulation of particles above the poles, while the troposphere contains less particles than it should. So in a new version, we reduce the number of internal interpolations by keeping the eta coordinates intact instead of converting it to like an internal meter coordinate system. And this solved the issue on short time scales, as you can see on the right side. So this is the 9th week. But we still find density distribution problems after a year of running Flexbot, and we end up with too many particles in the troposphere and too few in the stratosphere. So we're still working on that. We already made a first version of the LARA data set, which Katharina Baier, a PhD student in our group, has used to study the energy transport of air coming from the equatorial Pacific. So she tagged particles from this region and traced them 20 days forward in time. And then she compared it to the air that was not tagged. So here the gray box in the plot shows the region where particles are selected from, and the colors show the tagged to total air mixing ratio. So the darker the color, the higher percentage of tagged air is. So you can exactly link air from the selection region back to the tropical Pacific. Yeah, you like far away, you can trace it back to the tropical Pacific. And the same can be done when looking at the properties of these air masses that these air masses carry. So here you can see how the energy and specific humidity propagates from the equatorial Pacific into the rest of the world. So on the left is shown how energetic the air is that passed through the equatorial Pacific in the last 20 days as compared to air that wasn't. So for example, the air that passed through Central America is more energetic if it originates from the selected area than the air that came from other regions. On the right, is the same is shown, but then for the specific humidity. And here you see, for example, that air that originated from the equatorial Pacific is drier than other air in South and Central America. So Katharina Baier's paper describes in detail how this differs between like El Nino and La Nina periods for different regions, including vertical profiles. So I strongly recommend you to read it if you're interested once it's published, which probably will be soon. So in summary, the LARA dataset is a translation of the Eulerian ERA 5 reanalysis, which will make it easier to study transport of mass, energy, and moisture through the atmosphere. And the output will be particle-based in NetCDF format and cover a range of properties as listed on the slide. Well, thank you for listening. If not any questions, I'd be happy to answer.
Thank you very much, Lucie. That was really interesting. Sounds like quite a challenging endeavor to do all these Lagrangian computations. So let me see if there are any questions. Not yet, so I encourage you to write that someone is starting, but in the meantime, I was going to ask about what is the most challenging part of creating a Lagrangian reanalysis? I guess in a way you are translating an already existing Eulerian one to a Lagrangian framework. It is not the same as the creation from scratch from models and observations of a Lagrangian reanalysis, right? That would be more difficult, I guess.
Yeah, this is much more easy since we use the existing ERA 5 data set. So the most of the physics are parameterized, like the turbulence and the convection, and the rest is really just tracing the air through the well, you know, the wind speed. So you really just interpolate, you know, particles through through time. Yes. So, but the most, well, for this specific, the most problematic thing is the actual, to keep the density distribution the same as like the particles need to be distributed where they should be, right? That it shouldn't be that there's like gaps of air where you don't have any information. Also, when they are not, when it changes the density distribution, it also means that something is going wrong.
Yes.
So, so I guess like very small errors over, you know, years of running this become larger and larger. So I think just making it so that it doesn't that the density profile will stay the same over longer periods of time, I think is the most challenging part. So, yeah.
I think this is slightly related to Hao's question now that we're talking about density. Hao asks, how do you define the air particles? Is it by the density of the initial state at each grid point?
So the particles, they, so we just have the total mass of the atmosphere. Then we divide this mass by the number of particles, and then we put the particles where, according to, you know, following the same density. So the number density of the particles is the same as, is equal to the air density, or actually the actual density, because they have the proper mass. So does that answer the question?
I think so. If not, how can write any follow-up? I don't see any other questions yet. But why is that? We're on time. So if anyone else has a question, Daisuke Hotta has a question. Is particle tracing deterministic? And then he says, advection is nonlinear, and a small perturbation to departure points can dramatically change the particle position at, say, 10 days later. Something like you were saying about the great propagation of errors. It says, tracking many particles with slightly perturbed departure points can be useful. So what's your opinion on that?
Let me see if I understand correctly.
You can also see it directly in the joke pads.
Yes. Yes, so there is, so we parameterize, for example, the turbulence, so there is like some randomness in it already. So mostly in the PBL, but we also have turbulence higher up, which yeah, but they are parameterized. So there is like already some randomness to it, also in the convection. So does that answer the question? I'm not sure.
I guess so, because yeah, he was talking about this deterministic versus stochastic modeling, and you're saying that it's an hidden stochastic component in the parameterization. Finally, a quick question from Carlos Lopez. Are these particles allowed to deform and dissipate?
No. So the mass stays constant over time. They don't disappear. There's no new particles coming alive. They are the same from the start to the end. We do it in different periods of time, though. So over 7 years to you know, because it runs faster if I can do multiple at the same time, and then have like an overlapping time, so you can stitch them up if you want or need.
Excellent. Those were very interesting questions. So thank you, Lucie, again for your participation. And now I hand over to Marcin Krust